Hello all, this is Maleeha Abdul Aziz, Assistant Professor, Department of Electronics and Communication Engineering, Rajagiri School of Engineering and Technology, Kochi, Kerala. In this lecture, we shall look at yet another important circuit theorem, reciprocity theorem, as a part of Module 2 of ECT205 Network Theory. The topics covered will include the theorem statement, steps to prove the reciprocity theorem for both DC and AC circuits. We shall also look at examples for the same. The theorem consists of two parts, each a dual of the other. The first part states that in any passive linear bilateral network, if the single voltage source Vx in branch X produces a current response Iy in branch Y, then the removal of the voltage source from branch X and its insertion in branch Y will produce the current response Iy in branch X. Another way of stating the theorem is to say that the interchange of an ideal voltage source and an ideal ammeter in any passive linear bilateral circuit will not change the ammeter reading. The second part of the theorem states that in any passive linear bilateral network, if the single current source Ix between nodes X and X prime produces the voltage response Vy between nodes Y and Y prime, then the removal of the current source from nodes X and X prime and its insertion between nodes Y and Y prime will produce the voltage response Vy between nodes X and X prime. In other words, the interchange of an ideal current source and an ideal voltmeter in any passive linear bilateral circuit will not change the voltmeter reading. A pictorial representation of the theorem is shown here. Suppose a voltage source is connected in series with R1 and an ammeter is connected in series with R2 so as to measure the current through R2. Now, if we interchange the excitation and the response, we find that the ammeter produces the same reading as in the previous case. This holds true even if the excitation is provided by a current source and the voltage measurement is conducted. If we are to prove the reciprocity theorem for a given circuit, we shall follow the given steps. Firstly, the response due to the excitation shall be determined using mesh or nodal analysis. After that, interchange the branches where the excitation is applied and the response is determined. Perform the analysis to find the response again. Verify that the responses match in both cases. Let us now visit a few examples. Here we see a simple DC circuit with a 24 volt excitation. The current through the rightmost branch is measured. Since the voltage across the branch is 24 volts, the current I is given by 24 by 6 plus 4 amperes is equal to 2.4 amperes. Now, to verify reciprocity theorem, we place the excitation where we previously measured the current, determine the current produced in the middle branch. Since the leftmost branch is now short-circuited, all of the current flowing through the rightmost branch flows through the middle branch, that is, I is equal to 24 by 6 plus 4 amperes, which is equal to 2.4 amperes again. Thus, the response is found to be same in both the cases. In the second example, again a DC circuit, we shall resort to nodal analysis to prove reciprocity theorem. Let the bottom node be the reference node and the potential at node A be V. The nodal equation is given as V minus 10 by 20 plus V by 5 plus V by 30 is equal to 0. Solving for V, we get V to be equal to 30 by 17 volts. I, the current through the branch containing the 5 ohm resistor is V by 5 is equal to 6 by 17 amperes. In the second circuit, obtained by interchanging the excitation and the response, the nodal equation is given by V by 20 plus V minus 10 by 5 plus V by 30 is equal to 0. Solving, we get V is equal to 120 by 7 volts. Now, I is equal to V by 20, which is again equal to 6 by 17 volts. Hence, reciprocity theorem is proved. Note here that the nodal voltage, although is different in the two cases, the measured response is the same. In the final example, let us prove reciprocity theorem for an AC circuit. Here, we are providing the excitation voltage in the leftmost branch and measuring the current response in the rightmost branch. To do this, we find the input impedance or the equivalent impedance looking through the terminals across which the voltage source has been connected. We call this Zin. To compute Zin, we find that the 5 ohm resistor is in series with the parallel combination of the series inductor resistor and series capacitor resistor combinations. Now, the current sourced by the voltage excitation can be calculated as I prime. The current through the rightmost branch, I2 prime, can be computed using current division rule now. I2 prime determined is equal to 0.597 angle 162.64 degree amperes. Now, we move the excitation to the rightmost branch and measure the response at the leftmost branch. To do this, we again compute Zin. The 5 ohm resistor is in parallel with the series combination of the 1 ohm resistor and inductor. This network is in series with the 4 ohm resistor and capacitor. The input current I double prime is then computed as Vn by Zn. Following that, we determine the current in the leftmost branch, again using current division rule. Here again, I2 double prime is equal to 0.597 angle 162.64 degree amperes. Therefore, reciprocity theorem has been proven for the given AC circuit. To summarize, we have learnt to state and prove the reciprocity theorem. In a nutshell, the theorem tells us that when the cause and the effect are interchanged in a passive linear bilateral network, the magnitude and the phase of the effect remains unchanged. This holds good for both DC and AC circuits.